just a material, and I can print pretty much anything you like. Yeah, we print ears all the time. So when there's demonstrations, we like to print ears.
Print ears.
Yeah, it's quite
like the outside, like the pinner.
The whole thing from the ground up. It takes a while. But it's also a miniature version, but it's an ear. It's a bioprinted ear, but again, it's something that looks like an ear. It doesn't function as an ear.
Well, it's the outside of an ear, right? It's
like
the flappy bit.
Yeah, but even then, like, it doesn't really function as the flappy bit of your ear because it's based off it's based off collagen. That's it. What I used.
Hasn't got skin on the outside of it, and
skin hasn't got all the vascularization, hasn't got all the nerves, hasn't got many things. So it looks like something, doesn't mean that it functions like something. I think that can give like a misconception to people that actually we can do so much, but really, like, it's still quite far from what it should be. I realise my screen is quite dark.
That's all right. Yeah, go grab a light.
Oh, that's it.
Yes.
Yeah,
you can see the full extent of your lockdown hair now.
Yeah. I won't take it off. I'll take it out. It goes everywhere.
Oh man. Yeah. I'm not doing a top knot.
No.
No.
Well, no. I actually have had a haircut.
Have you?
Yeah, I actually have. He just took off the size of the bottom.
Nice. Yeah. We got a question from HoloScript. I'll read it out. It says, could this technology be used in theory to help with blindness and repairing optic nerves after trauma, instead of waiting for something crazy like nanotech, which is another big thing.
Well,
it's always talking about.
Nanotech is much crazier than bioprinting. I mean, maybe slightly more crazier. I mean, there's a lot of nanotech going on in my department as well, and they do some really cool stuff with cancer at the moment. So they're looking at some nano stuff to detect cancers and much quicker than we can currently. So I won't say it's completely crazy, but yeah, for optic nerve. So I mean, I suppose yes, you could try and it will be very difficult at this time, but eventually yes, you could. If you knew exactly the nerves or the optic fibers that were damaged, and if you could recreate those artificially, I suppose you could simply switch them out for a fresh pair of optic nerves, essentially. But I think that bioprinting would be the way to go about that. I think there's some interesting genetic work going on with that. So looking at some gene therapies with optic nerve issues. I think maybe not optic nerve issues, but definitely with blindness in general. I know we can actually cure blindness using genetic engineering. I don't know if you came across that story recently.
I haven't. I have to look at the literature, Naheem.
Yeah, there was a CRISPR study where they did something and they were able to cure like a heritable blindness.
That sounds doable. Like gene replacement therapy and things like that.
That's it. Yeah, gene replacement therapy.
Yeah.
So I think those technologies are more kind of geared towards that. Bioprinting is more sort of for transplantation, yes. But this is more. It seems more suited to other technologies rather than bioprinting.
Something probably a bit more structural, I would think. If you've got you've got, I don't know. I mean, you said you're working on like tracheas and things. If you've got like a cancer in your trachea or something, or need a replacement, then so effectively that's just just a tube, but it is effectively it's a secondary structure, right? That's what you're trying to print.
So, but I think it's also common as well because we have this cool new technology. It's very common to want to apply it to everything.
Of course.
And I wanted to fix all the issues that we currently have. But yeah, I think there's so much out there as well. I mean, that it's important not to forget all the other technologies and all the work that's going on. And I think there's definitely more work that's more suitable for what the question was for optic nerves.
Yeah, man. I mean, you and I kind of cross paths. Because you got into the drug discovery game, or partly funded by the drug discovery game, I should say. So you're kind of working towards, well, I guess some of this 3D printing technology being able to be used in the drug discovery industry. Do you want to allude a little bit onto that and how that might how it might benefit other industries? We've talked about transplantation quite a lot, which I guess is the ultimate kind of therapeutic goal. But there are other applications that people might not know exist, off the bat.
True, yeah. So I personally don't work towards printing anything that's going to be transplanted into a person. I work towards printing something that we can use to replicate human tissue and to use for drug discovery. So the idea being that currently the models that we have are very restricted in their translatability to the human tissue. So in more than one way, they lack immune cell components, or they lack vascularization, or they lack cell types that are missing. So in all these ways, the models that we currently have are limited. So what I'm hoping to do is use bioprinting to produce models that are more realistic and that better recapitulate the human environment, the human tissue environment. And by doing so, when we then go to looking at testing new drug compounds, we'll have a better likelihood of finding the ones that are going to work in comparison to the ones that won't work. We'll be better at finding toxicities of these new drug compounds. So that, I think, is a very promising area right now. It's much more feasible for us to have 3D printed tissue constructs to use in drug discovery within a couple of years, as in comparison to having something that we can transplant into humans. I don't see any reason for why we won't be implementing these things into drug discovery in a couple of years. The main hurdle there is validation of the models that we make, regulatory hurdles that we need to pass, and really that the regulatory systems that actually have to be updated, because the technology and the tissues that we're making don't really not really compatible with what's currently there in the regulatory system, that the hurdles we need to cross. So they really need to now kind of work with us to create a new framework for validating these new models. That, I think, is a big hurdle. But once we can get through those phases, and then there's no reason for why things that are printing now in the lab can't be used in drug discovery in a couple of years.
So when you're talking about validation, like what how close are we? What are the major differences? Because you said there's no there's no vascularization, there's no nerve component of what you're doing at the moment, but surely it's better than what we've currently got, which you could just say is cells in a dish.
Yeah. In definitely in some ways it's way better than what we have. So for example, we can print different cells. We can print multiple cell types, 3 to 4 cell types together in a very repeatable way. So it's the same number of cells within each well, printed in a very specific structure that we can recreate. And in that way, we can produce tissues with at least on a macro level. So even on the micro level, they look, even the face validity is much closer to that of the actual tissue. But at the same time, there's pros and cons. So cons are time, like the high throughputness of the models, the cost and the feasibility of the models in general. I mean, these models, first you need a bioprinter. It costs many thousands of pounds, whereas you can just bind some cells and produce a simpler model, which will work to some degree looking at toxicity, for example. So there's, you've got to weigh these up. So once we have the models where we can also produce them at a particular price, and we can have them in a very high throughput format, then they'll be undeniable. Then there'll be no reason for why we're not using them. So there are still some other limitations as well that we need to get past. But I think they're a lot more. Sorry,
No, carry on.
But I feel like it's a lot easier for us to answer those than it is to fix the issues regarding transplanting tissues, because there's a whole minefield of issues we've got to fix there with transplantable tissues. So I'm more confident in what I do, basically. That it's going to come somewhere.
So, in terms of, sorry, I've got a question. No, I wrote down this question. You said this. You said you got to buy a bioprinter, right? So, do you have to have a special printer? Is it like a special thing, or is it effectively? Could I just go and buy like a regular 3D printer, and it's just the material you're putting into it, or is it?
No, so it's a bespoke. Well, it's not. You can buy it commercially, but it's not a regular 3D printer.
No.
So the main difference is the extruder. So for a regular 3D printer, it has an extruder which prints polymers.
What's an extruder?
The extruder is essentially like a needle, a nozzle, something the tip that the material is extruded through, or extruded in other words, like just pressure. You're pushing something through a nozzle. So that nozzle usually is heated to around 230 degrees for printing polymers, which is not feasible with cells. So the main difference there is with bioprinters is that it doesn't have that. So there's many different ways. There's still extrusion bioprinters, but these involve a piston or a screw pushing on effectively a syringe, which then extrudes your material mix, which is your biomaterial in your cells, through a nozzle, and then while it's being moved, computer controlled in 3 axes. You can also have like stereolithographic bioprinting, whereby you have a sheet, like a hydrogel construct, which is like a sheet, and you basically punch your shape through the sheet, and the gel drops through the sheet onto kind of a printing bed, and then by doing that, you can then produce a construct. It's very interesting.
It's like dripping it through.
Dripping it through, kind of droplet, yeah. And there's also there's other types. There's some very cool types recently that were published. So that was called digital light processing. So that was it might be a bit difficult to explain, but they did some really cool stuff with it. Essentially, it was published in Nature a few months ago, and they basically use it to non-invasively bioprint tissues into a rat. So they basically they use infrared light, which can it can travel through tissue.
Right.
So by using infrared light, and they injected the hydrogel construct, the hydrogel, just the hydrogel itself, the biomaterial encapsulated with, I think they used mesenchymal stem cells. So they injected that into the rat in, let's say, I think it was subcutaneously or under the muscle, essentially. They then fire the infrared light onto the skin of the mouse, and then it then cross-linked the gel, which was within the mouse, and cross-linked it into a particular shape. So
into a 3D shape.
To a 3D shape. So they did that by using a chip. So the infrared light was passed through this chip, and the chip then it determined how the infrared light was being shone at the tissue. So it then only, it was very simple shapes, and we're talking about cylinders, like little circles or little squares, and it would then be able to control that infrared light to print the whole layer at a time, and then produce this 3D printed construct within the tissue without actually having to print, without actually having to go into invasively go into the tissue. So there's some very cool methods.
My brain hurts.
Yeah, I probably did a terrible job explaining that.
No. So effectively, you're saying that they can effectively transplant a cellular structure in without having to transplant anything. Build it from the inside.
Yes.
That is
in very old ways. Yes.
I'm just trying to think how useful that would be, but I'm sure that someone smarter than me will know exactly how useful that will be.
It's amazing if you could do that. I mean, you could heal injured tissue defects without actually having to do surgery. So the bounce for a patient coming back from that would be way quicker than them having gone through a surgery on their liver, for example, if you could recreate that tissue from the inside. But obviously this is a big leap forward. Well, what we can do at the moment is use this. It's called DLP, if you're interested, DLP printing, and we can use this in a very particular way, in this way, to produce these very simple gel constructs, which actually they were encapsulated with stem cells, and stem cells over a period, I think, of 2 months, they actually differentiated into different, I think it was chondrocytes and stuff, and they were then able to excise them out and show that there was no excessive inflammation around those areas. So it kind of did work. But yeah, so there's some very interesting bioprinters you can do. That I think that was more of a bespoke model that I think was out of MIT that they did. So I don't think that's something you can buy. But generally, you can just buy bioprinters commercially that are simpler than that. But you know,
I'm gonna have to go and have a look up this in situ.
It's non-invasive. No, yeah,
I'm writing it down. Non-invasive.
Non-invasive bioprinting. Yeah, it's a very cool paper. That was quite recently. I think it was in Science or Nature. Actually, no, I think it was in Science. Yeah. So yeah, there's some cool stuff that you can do, but again, so even with that, I mean, there's certain issues. I mean, they used nano initiators. So these are like little nanoparticles, which converted the infrared light into UV light, which the UV light was then used to cross-link the gel. They used gel MA. So they converted the infrared light into UV light to then cross-link the hydrogel. And those nanoparticles that they used, they were called up-conversion nanoparticles, where they take in infrared light and they convert it to UV light. Those can be potentially toxic, for example. But they didn't show any toxicity in the paper, but in general, those nanoparticles are toxic at a certain concentration. So the feasibility of using those for like larger tissues is not so great. But the idea that they proposed that we could actually use something resembling those nanoparticles to convert the infrared light to UV light to crossing the hydrogel is an interesting idea. So, yeah.
I think you'd have to get a safer way to crossing the hydrogel.
Yes.
If, Yeah. I don't think anyone's going to want UV light inside. Although Donald Trump did say, about treating COVID by getting UV inside the body.
It's true.
So yeah, maybe smarter than we think.
maybe, but there was something actually. They said that UV light does actually kill the virus.
Yeah, I read that. I think it was UVC.
UVC.
Yeah, I think it was. It wasn't. There was a theory put forward. I don't know if it's been tested, that actually it's harder to transmit the virus in the daytime than at night because of the UV that's kind of just from sunlight. But I don't know where that research went. So.
No, but maybe he was onto something. You never know. You might have government scientists. They might be working on something and they're not sharing with the rest of us. So.
He just can't share it. That's what it is. It's all kind of he's like a kid with a secret.
Yeah. But if anyone was going to share it, it would be him. So it kind of makes me think that it's not. If anyone was going to tell us that there were aliens and all this, it would be Trump. So
he'd probably do it on the way out, wouldn't he? He'd like if he got voted out, the last thing he'd do is just be like spill all the beans, maybe.
Everything's all the conspiracies are true. The world's flat.
Giraffes aren't real.
Yeah.
So 3D printing, right? If I'm taking 3D bioprinting, what I've taken from this is that it's still in its kind of fledgling days.
Yeah.
But we are able to, or you are, not we. You are able to print structures that have human cells in them, and you can print them into certain shapes that could possibly one day be the road to transplantation, and building transplants for people. And at the moment, another application is this idea about building more artificial human systems in order to test physiology and treatments and drugs and this kind of thing in a more reflective and representative kind of way. Is that fair?
I think that's very fair. Yeah. I mean, there are other things that as well that they use. So for like surgical instruments and tools, we can now it's bioprinting. It's also more 3D printing, I would guess, where we can print like surgical models for training purposes, for like medical students, for them to learn. You can actually now it's sort of bioprinting. It's more 3D printing, but we can print very realistic tissue models for them to practice surgery on, so they can have rather than like a plastic dummy that's basically not very representative. You can print very more complex tissues that they can practice with. The tools like forceps, clamps, scalpels, we can print all those. So, and then there's the kind of more fringe groups, which are more kind of they're quite blue sky at the moment, but it's sort of interfacing bioprinting with like handheld printing. So there's like bioprinting pens. So you basically, a surgeon could just go in during the surgery and have a sort of handheld thing that he could use to print tissues with. And again, these things are they're speculative because they use UV light, they use certain things that are quite toxic at the moment. But the idea being that these printers don't have to be on a desk in a hood somewhere in a lab. They could be more portable, and so much so that it's literally a pen, something that it's basically a syringe full of cells that a surgeon could use, to move around and to print stuff and to do things.
It's almost like could patch holes in people, like
almost so, yeah.
Just almost color it in.
Yeah, color it in, and then it'll cross-link the material in that straight away, immediately, and you ended up with kind of, even if it's like a wound dressing or even if it's something more invasive, you've done that really quickly, you've done it straight away. So yeah, there's some other interesting ways that people are using bioprinting, I think.